So welcome everybody to lecture 7, Databases and Information Systems, which can also be taken as information retrieval. Fewer people than usual, end of the year atmosphere. So I will say something about your experiences with the last exercise sheet, which was 2 weeks ago. I hope you enjoyed the free week, or at least free from this lecture. It was about knowledge graphs and Sparkle. And today we will talk about fuzzy search, and we will see all about that in a second. Fuzzy search, edit distance, qgrams, qgram index, and so on. And the exercise sheet will be to implement this with a very nice data set, which I will show you in a second. First, about the last exercise sheet, which, as I just said, was 2 weeks ago. RDF Sparkle is an awesome, interesting exercise, also challenging for some. Here are some quotes. It has been very challenging, but fun. So we have been doing 3 lectures on databases and then knowledge graphs. Knowledge graphs kind of built on databases. It's like databases below, but a more meaningful standard and format. Needed time to get used to knowledge graphs in Sparkle. Yes, that was one of the points of the lecture. Fascinating way to structure and query data. Somebody updated the engine to add support for optional, and I will say in a second why. Exercise 3 was challenging and a bit annoying because you were just given the data set with these Wikidata style IDs, where the IDs are just numbers, and you have to find out what they mean. Very curious to see how exercise 3 can be solved with one query. I will show you in a second. Overall, this sheet was very difficult for me, so some people were struggling a bit. Would be nice if the sheet changes would be communicated. We did, Sebastian, we did communicate the sheet change, right? I think we did. Would be nice if you subscribe to the forum, and I think we did, because we always pay attention to that. And yeah, the youngest CEO that was query exercise 2 is a convicted scammer. So let's look at that. Let's go to the solutions, which are also online now. So let's go back one. Solutions, sheet 7. This is sheet 6. Sheet 7 is what you have to do now. There we are. So what I already did for you now, because that takes a little while. So this is just to create the databases from the TSV file which we were giving you, and let's have a very quick look at this. And some of you, and absolutely, if you didn't do the exercise, you have to do it at some point, because I think without doing the exercise, you don't really understand this stuff. And for sure, this will be a topic in the exam. So this was the one data set, just triples, but triples which you can read, so sites work, Dungeons and Dragons, and so on. And then there was, which we called complex, we could have also called it realistic. This is the data like you get it out of Wikidata, so you just have IDs here, and now you would have to, we could just search this in the data set here and see, or maybe just grab it, and somewhere there will be a triple saying which label this has. Okay, this now also gives us things which continue. So maybe here we need a tab. Yeah, okay, so here, Changeling the Dreaming, not sure what it is, maybe a movie or something. Yeah, you just get these IDs, and then you have other triples which say what's the name of this thing. Oh, here we see tabletop role-playing game. So to find out what things mean in this data set is a bit more complicated, which was exercise 3. Okay, so these were the data sets given to you, and first step was just to build a SQLite database out of this, what I already did now, just before the lecture started. Takes a little while, like 1 minute or so, longer for the complex one, faster for the simple one. Let's maybe also quickly count. These were not so small data sets. I mean, it's fun with, so that was like, that's I think 60 million. And let's look at the simple one, 17 million. And then what you could do, then the task was to write a Python script, a Python program where you enter a query. So this was the correct Sparkle query for finding the CEOs. So it was people who are CEOs. You had to find that there was a predicate Chief Executive Officer, so pretty obvious. Date of birth, place of the country, United States, because there were just more of them. Gender, and then order by birth date and take the first 10. So that was the query. And then your task was to write a script, Sparkle to SQL Pi. Let's just take a look at the argument it takes. 2 arguments, the database, the SQLite database on which to ask the queries. So that would be, in this case, Wikidata simple DB, what I have prepared. And then just the Sparkle query, which you see above. And now this Sparkle query is translated to a SQL query. That was the task, to do that automatically. And here you get the result. And the funny thing is, indeed, that the 2 youngest of each gender are convicted. Yeah, they did something which they shouldn't have done, Elizabeth. Yeah, so I don't know what that says, but that's just how it is. Okay, and then now the second one for the monarchs. Monarchs of the British monarchs. It was already written on the exercise sheet that it's not so easy. And here in the master solution we also have 3 queries. So this was 1 query, so you had to find out that you have this predicate P39, and let's maybe look that up in Wikidata. P30, let's go to Wikidata. I'm not sure how you find predicates here. Let's just do it like this, P39, position held. So that's position held, you have to find that out, but another way to do this is, how do you find, you just take someone which you know, like maybe Queen Elizabeth II, and then you look in the data where it says what she was, and then you find, oh, it's position held, it's where, and then it says monarch of this, and so on. So this is the way how you could have found this out, or you find it, just search your way around the data set. So you see she's a monarch of a lot of things. It's called the Commonwealth, and somewhere down here is, where is it? So many that it's hard to find. The United Kingdom, and if you see the mouse over here, it's Q9134365, and this is indeed what we have here in this query. And now let's execute that query in the same way by just feeding it now into, I have to call the Python script, Python Sparkle, and now I have to Wikidata complex DB. And note, this is already a lot of technology coming together here, right? We have our SQLite database. We could have even taken our own database, but we made it simpler here. So you have database technology here. You put in a Sparkle query, it's translated to SQL, then executed on that database. So pretty complicated stuff already, or not complicated, but using a lot of technology. So it's translated to this query. And now, indeed, you get Elizabeth II, but it doesn't go further than George V, who came to power in 1927. And the reason is that it changed over the time what Britain is. And I think several of you found that out. So if we look at the second query here, now here it says Q1, let's just look at that up in Wikidata. We enter this. This is now monarch of United Kingdom of Great Britain and Ireland. So before that, British was that. And if we ask that query, now we get everything from George V back to George III of Great Britain, but it still doesn't go all the way back. So you have a third query, And if you ask that, let's look what the Q is here. So they all have the same form, but it's always monarch of something else. So it's a complicated thing, this British monarchy. Now it's just monarch of Great Britain. So you have monarch of Great Britain and Ireland, and then monarch of United Kingdom, I think, yeah. And if we do that, now we get it back to N of Great Britain. And before that, that was the last question on this sheet, something completely different. And now the big question was, how do you get all this in one query? I'm not sure if many of you said you tried, but you had a hard time doing this. So what's one way of doing this? Well, one way of doing this is you look this up, and then you look, okay, up here it says, is this part of something bigger? Or you could have and then you find out, for example, that this is part of monarchy of Great Britain or part of British royal family. If we click on this, British royal family now, Q645968. And indeed, I think there was a hint in the last 3 triples of the data set, so it's a little Easter egg here, we made it the last 3 triples actually say that these 3 things, monarch of this, monarch of that, monarch of that, are part of, and this is just the British royal family. And this, so indeed, you get with this one query, let me just do this here. So now it says, position held is something, so you introduce a variable here, and the something is, and this is the predicate for part of, and this is British royal family. Or maybe you could have also taken, I think that would have also worked, monarchy of Great Britain. But I don't think, maybe the triples were not in there. So let's try that query by just feeding this into our script. And now we get this. So that's the query, that's the SQL translation. And now we get all of them back to 1707. So, and that's actually quite typical. And that's also why we did this as the exercise. So you have to understand quite a bit about the collection to find this information. But it's also very interesting. And you learn a lot about history. So what happened? Why doesn't it go further back? So I mean, there are kings somehow in this area of the world which will go back to before 1000, I think. I think there is a list of English monarchs. Let's do a little bit more of history. The English monarchs start in 849. 849, and then they go until 77, starting with Anne. So what happened in 77? Actually, several of you researched this a bit. So Anne of Great Britain came to power, it seems. Yeah, that's true. That just happened in 17. The Acts of Union were passed. So I think that's what happened. So before that, you had Kingdom of Scotland. So you have this here. You have the monarchs of England, and they go back to 895, and I think let's just list of Scottish monarchs. You probably also have a list. So now, and sometimes they were the same. I don't know how far does this go back. 858, so about the same. So you had all these different realms, and then at some point they were unified, and this is what happened in 1707. At least some of them. Scotland and England united to form Great Britain. What a time to be alive, yeah. 1777, I suppose, at least on one day, there might have been rain falling. Yes, I agree. The question on the sheet was not very specific. And somebody wrote, I asked a British friend about the monarchs, and they did that before they worked on the exercise sheet to find out how do I get them all together in one query. And she told me about the Acts of Union in 1707, before I even noticed the question at the end of the sheet. So that is my final answer. And yes, you won €1 million. Congratulations. Okay, so I've also shown you the, as one of you noticed, so why isn't the That was the optional remark. Why is Prince Charles, or King Charles, it actually became king, not here? Well, because there is no end date, right? It's just start time, no end time. And to have the end time, you would need the optional. I think we talked about, or it would be like this joins, which we talked about in the data-based lecture, or optional. And then you also get, I don't know, should we do that? No, I think we should continue. So somebody just implemented it because it's relatively easy, and then you just get you also get those which don't have an entry in end time, and you will also see Prince Charles. Okay, let's continue with the lecture and a new topic, which is related. And so the next 3 lectures will now kind of tie everything together, which we have done so far. And so the next 2 this exercise sheet and the next 2 will be really interesting because they combine kind of everything to one product, which I think will be very fascinating to see. So we start with fuzzy search, and fuzzy search is, I mean, it's doing, it's doing what I have been doing here in Wikidata. So I was looking for something, Queen Elizabeth. I mean, you do that all the time. I mean, this is the lecture databases and information systems, and a very common aspect or feature of information system is that you have some field and you want to find things from some big list. So here it's just all the entities, 100 million entities. I typed Queen Eli and I find Elizabeth II. And another feature, maybe I don't know how to write Queen and I write it like this and I don't find her. So actually it would be nice if I can also make typing mistakes, but I can't on Wikidata. But for the exercise sheet, we should allow this. Thank you, Frank. And this is our topic today. Not just to type something and get prefix hits if it's correct, like Frei and Freiburg, but you're also allowed to make mistakes. So there are like 3 variants. Prefix search, this is what the Wikidata page does. Here you just do a complete match, so you can type something, but it has to be the whole thing with mistakes. And what we do today is actually fuzzy prefix search. You just type the beginning of something, you can even make mistakes there, and you still find what you're looking for. That's what you really want, and that's what we're going to do today. And we have prepared this wonderful, or Sebastian has prepared this wonderful data set for you, and let me show it to you. It will be the data set for the next 3 sheets, and it kind of belongs or is not independent of what we have done so far. It's the entities from Wikidata, and it's like the entities from the data set with which you have worked in the last lecture. And let me just show it to you. I think I have to go back here, public code lecture 7. You can download it from the wiki. I've already did that here, and it looks like this. Maybe I make it full screen again. So in the first column, so it's name, score, synonyms, and so on. The first column, now you just have things from Wikidata. Let me just cut the first column so that's the main information. It's just these entity names, starting with a country here because it's somehow ordered by popularity measured by number of Wikidata, Wikimedia links on something. So now you get all kinds of entities here. Names, people, chemical elements, whatever. But there's also more information here which you can but do not have to use, or partly you have to use it, partly you can use it, like a score. So kind of proxy for popularity. Synonyms, so other ways how to search it, that's optional, but it's very interesting to use. Wikidata ID, a short description, and more information which will be relevant for the later exercise sheet. Okay, so that's the data set, and our main goal will be to solve this fuzzy prefix search. And the challenge will be to do this, we have to solve 2 challenges. When you allow typing mistakes, now you have to say somehow, okay, what's what's relevant, it's like in the first lecture, what's similar to what I have typed. We need a notion of relevance, and then we will see it's not so easy to make this efficient. So we need to have a built-in index. So it's kind of what we did in the first 2 lectures, just for a different problem now. Very briefly as a background, so where does this list come from? A list like this, there could be many sources. Here it comes from Wikidata. One typical source for search engine, Google just knows what people search. So when I type something on Google here, Google does the same thing, right? Now it's just this completion here will not only be from a list like Wikidata, it will be from queries, which it will be a combination of such a list like from Wikidata and what people frequently search. You could also maybe have a collection where you don't have a query log yet, you don't have experience from people searching it, then you could just search it for common phrases. That's an interesting problem by itself. I give you any text and now you want to find interesting names in there or phrases. Or what we do for the exercise sheet, you take some knowledge base and take a list from there. So whenever you have a new problem, you should first look at the simplest solution to see maybe it's good enough. And what's the simplest solution? Well, let's just do what I did here again. Let me cut the header line and let me just. So this is now just the names, and now I can use a command line facility like grep. So let's just look at grep. I'm looking for, I could just do grep. I'm looking for Frei, maybe I'm looking for Freiburg. Oh, you see a lot of things here. So that's now just doing prefix search. How big is this file? It's 25 megabytes, so and that's a very fast machine where we're here, so maybe type a little bit more Freiburg. Yeah, and now you see I also get Freiburg im Breisgau. So you could just do grep, and it's not that bad if it's not very large. There's also agrep for approximate grep. Let's try that, agrep. And with agrep you can specify how many typos. So I'm just allowing a grep with 2 typos now, and I'm typing let's see. Okay, I don't find anything, that's too many. Now I find a lot, okay. Because I allowed, so that's also interesting already, right? If you allow 2 typos, you get things which are, so you also have a ranking problem here. You get a lot of things. What do you show first? Let's maybe only allow. I still get a lot of things. Yeah, but anyway. So you can use grep, you can use agrep, and they are not so bad. They're pretty fast. Of course, they're written in C, and the file we have just seen was pretty small. And what do these tools do? You can also use them to. Yes, there's a question. How's the type? That's what we will do next in just a second. Yeah, exactly. How is it defined that I can make 2 mistakes? A very appropriate question, and the next part of the lecture is about that. 2 errors. Next slide. Okay. Next slide. Is it the next slide or the slide after that? So let's first, what's the time complexity of this simple solution? As I said, first understand the simple approach. Simple approach is you just go through everything. So you have a number of records, doesn't have to be name, can be anything with text, and then you have the time for checking a single string. So very simple, it's just number of things times time. Now, how long does it take to find if such a thing is a match? It's actually not so easy. If you would do it in Python, I think it's 1 microsecond to just check, is this string, this other string up to, we will find out what typos mean in a second. What do we want? We want, just going back to this here, if you type something here, you don't want to wait a minute, right? You see it's waiting a little bit here, but you get a little bit of a wheel here. Yeah, and it's very annoying that you can't make mistakes here. So, typical number, 200 milliseconds is something where people say, yeah, that feels kind of instant. 50 milliseconds, it feels really instant. So this means we would be fine for up to 200,000 records. So for the sheet, we already have 1.6 million records. In reality, you have even more. This search is in a list of 100 million. So you need something better. But it's pretty good. Never underestimate a baseline if your data is not so large. And we will see, that's the rest of the lecture. So now we will talk about edit distance. This is our measure for when two strings are similar. So it's also called Levenshtein distance after Levenshtein, who already died a few years ago. And this is kind of a similarity measure between two strings, x and y, any two strings. How is it defined? We define 4 operations or transformations to get from one string to the other, and here they are. This is not blue, so we have to make it blue before we can continue. Otherwise, it won't work. They have 3 operations. One is insert one character, one is delete one character, and here I also give you the signature, and one is replace one character by another character. And let's just do it. It's like these riddles which you find in magazine, and I always take the same 2 words. So let's take the German word doof. Let me write it like this. And let's assume we want to get to another German word, blöd. So we want to get from doof to blöd with these operations. And let's see, how do we do it? So let's maybe go from, there are many ways to do it, and we will see a systematic approach in a second. We could, so the D, I mean, it's actually harder than it looks. I mean, it looks like D, we want a D in the end, but there's no operation to get a letter to the end, right? I mean, we could now delete all these 3 here's. It's actually, yeah. You can think about it yourself, how you would do it. Maybe you find a better way, and you should think about whether you find a better way. But for now, let me just replace. So that's now, and let me do that in. So what operation is this? Here I did a replace. I did a replace of, and let's start counting the position at 1 by B. Okay, now I have both. Now maybe let's replace the second one by an L. So that's bloof. The second one by an L. And now we could insert something. Maybe now it's time to insert the E. Blöf. And you see now I'm already there. So that would be an insert here. And the insert would be at which position? 1, 2, 3, 4. I'm taking the position where I inserted. I'm inserting an E. And here, this final operation here is again a replace. I'm replacing the last one, which is now position 5, by a D. And now, very important, so let me write it here, important. This does not show that the edit distance is 4, right? This only shows that the edit distance is, it could be smaller, right? Is it smaller? What do you think? There could be another sequence of operations. Maybe I wasn't clever enough. What do you think? Is there a sequence with 3 operations? What do you think? Think about it a little while. And you could think in both directions. You could think about finding a smaller one, or you could think about an argument why there can't be a smaller one. Any opinions? Maybe the edit distance is 3, maybe it's 2. And we didn't really make use of the fact that there is a D here, which is also there. We kind of just replaced the D and then D. That looks wasteful, right? So what do you think? What's the edit distance? 4, 3, less? Yeah? Okay, these were interesting thoughts, yeah? So you said looking at the same letters is not enough. I mean, there are 2 same letters here, D and O, but they're in the wrong order. D is at the end. Here becomes before the O, so look at the sequences of letters which are in the same order, which here would be only 1, right? Only the O or only the D. And then, yeah. And so you were kind of arguing why. And it's correct, you can't do it with less than 4. But it's very interesting that already for this simple problem, a string of size 4 and a string of size 5, it's not so easy. If I would ask you to mathematically prove that 4 is the best, I think you would have a hard time. These were very good arguments, but how do you turn this into a proof? And so let's talk a bit about this. So let's first introduce some simple notation. We will not go into super depth here, but at least I will tell you something about it. Actually, in Algorithms and Data Structures lecture, there's a whole lecture about this. So the empty word, you need a character, because if you just write nothing, it's hard to see. You don't know what is meant. So epsilon is the empty word. The length, you just denote it like by putting these vertical bars. Substrings, we just do it like this, so Python style, no, Python would put a colon here. So here we put dot dot, and we start indexing at 1. It's just in the math. It's nicer. Here's some simple properties. These are also popular exam questions, this or related ones. Okay, this was the wrong one. I need this one, yes. So why is that? Can you give me an argument? Why is it symmetric? Is it symmetric? Yes, I said it's symmetric. So if I go the other way around, why is the edit distance from doof to blöd the same as from blöd to doof? And is this true in general? Yes?
I think each step is reversible.
Each step is reversible. Yeah, that's a very good answer, yes. It's true, yeah, exactly. For every operation, you can find an operation in the other direction, which means the 2 correspond to each other. If you would have a shorter sequence in the other direction, you could turn it in a shorter sequence in that direction, so they have to be the same. That's how the proof would go. And I would recommend to just try to prove these. If you prepare for the exam, when you prepare for this exam, try to prove these little things. That's another simple one going, let me say you how do you get from the empty word to a word? Well, there are not so many options, right? You have to insert one character after the other, and that's the best you can do. You can always do it worse, like in worse, insert some things, then replace them by something else, delete things. But the obviously best thing is you go from nothing to a word with 5 letters, you just insert the 5. This just says to go from one word to another. If there's a difference in length, you need at least that many operations. One is of size 3, the other of size 7. You will need at least 4 operations because you have to add these. Every operation just adds at most a character. This is a little bit more complicated, and we will not go into the detail here. There's a recursive formula which I can only briefly explain. I would need a whole lecture or half a lecture to explain it. But that's the way to compute it in practice. So if you want the edit distance, then it's the minimum of the following 3. And we will turn this into a scheme to compute this in a second. So it's like the edit distance of where you just omit the last character of the y plus 1. You omit the last character of x and then plus 1. Or you omit the last characters of both strings and here take it plus 1 if the last characters are unequal, or if the last characters are equal. That's maybe the easiest one to see, right? If the last characters are equal, then one option is to just leave that last character in both strings and just see how you get from the parts before the last character of the one string to the other. So they are basically, what you're doing here is you're making assumptions, right? Let me briefly explain that. Maybe you're saying, okay, I want to get from x to y. There are 3 possibilities, kind of. I leave the last character here in y, so that would be and then, what this says is I have to replace the last character. Yeah, I think this formula is, let me try it anyway. So what this says here, the last operation will be to change the last character of y. This would be the case number 1. So I do everything to get from x to y without the last character, and then I do something with the last character, this plus 1. This is the same for x, and here this is the case when I do something about the last 2 characters. And there are no other possibilities. And so what you can see with this formula is that it will it's recursive, and it takes you from strings, from a problem with 2 strings x and y, to a problem that is simpler in the sense that at least one of the 2 strings is smaller. So the recursion actually makes sense, right? Here the y is smaller, here the x is smaller. Now when you again do recursion with this one, again one of the 2 will become smaller. So eventually you will, one of the 2 strings will be empty. And here's the base case, and that we know. If one of the strings is the empty string that we have just seen, then this is the edit distance for either of the 2 strings. If one of them is empty, it's simple. And as I said, the proof is not trivial. If you are interested, here is a reference to a whole lecture where you can see it, but you don't have to understand, you just have to know the formula for now. But what we should do, and what you should be able to do, is use that formula to compute the edit distance. And let's just do that. And actually gives rise to a schema, so the recursive formula, and let's just do it like this. So we went from, how did we do it? I will do the following. So let me take the same 2 words which I had in my example a few slides ago, and let me write them like this. So this is epsilon, the empty word. You will see in a second why I do it like this. BL blöd here. Okay. And now what I'm doing is let me just write some numbers here and then explain to you what I'm doing. So let me take purple here. So what I'm writing here And let me explain that to you. So what does this number mean? This is the edit distance from epsilon to the word do. So what I will have in this table is the edit distance for all combinations of a prefix of this word and a prefix of this word. So I'm looking at all prefixes. Let me maybe, so I'm looking at all prefixes here, and this is, so this is the edit distance. Here it's the empty word, so the smallest possible prefix of blöd, and here it's the prefix until u, and that's why I write the epsilon here, so that I can also get the empty word. And now, and that's obvious, if I want the edit distance from the empty word to something, then I just get 0, 1, 2, 3, 4, right? Because it's just the length of the prefix. So do has length 2, so it's just 2 here. And please do ask a question if anything is unclear. So filling these is easy, and it's the same in the vertical directions. So maybe why not also add that to clarify here. So this box is now, that's the edit distance of, and that's now from blå, the prefix until there, to the empty word, and that is 3, of course, because you have to delete 3 letters. And now let's see if we can do this together. Let's go back one slide and so what you have to do, let's turn this into an algorithm. So you take away the last character from one string and compute the edit distance, and add +1 from the other string +1. So you consider these 3 things here, and then you take the minimum of them, or you take away both letters, and then you add +1 or not, depending on whether the last character is the same. So let's just do this here. So what I have to do to compute this number here, so I'm considering these 3 here. So this is, should have maybe written this here. This is my x, and this is my y, as you can see here. So this is the first word. This is the second word. So this is, if I'm going, I want to compute something for this entry now here. So if I go 1 to the left, this is like taking away the last character of y. It's just one prefix before that. If I go up, I'm taking away the last character of x. If I go here, I'm taking away the last character of both. So what I'm doing, that's really what the formula on the last slide is saying. I'm taking the minimum of these 3, except, and I should say that again, that for the diagonal one, where I'm taking away the last character from both strings, I'm only adding 1 if these last characters are not equal. Otherwise, I can just take them away at no cost. So I have to pay attention. Here, D and B are not equal, so it's just the minimum of these 3 plus 1. So the minimum of these 3 is 0, and plus 1 is 1. And let me do one row, and then I will ask you to tell me the numbers. So I'm here, I'm taking the minimum of these 3, and I'm checking whether the characters are the same. O and B are not the same, so I indeed take the minimum. Otherwise, I would use 1 less here. So it's 2, 1, 1. The minimum is 1 plus 1. So that's 2 here. And here it's 3, 2, 2. O, B are again not the same. There is no B here, so I can, in that whole row, it will always be just the minimum of 3 plus 1. 3, and here it's 4. Now it's your turn. Well, what's the correct number here? 2, I agree. Here? 2? 2? because there's a 1 here. It's the minimum of these 3 plus 1. What is it here? 3. I agree. Here? 4. Yeah, that's correct. And here, now we have to pay attention. There's an O, but here O and D, they are not the same. So what is it here? 3. And now we have to pay attention. Now it's O here and O here. So what is it here? Yeah, it's 2. Exactly, because you can take, it's, yeah, the edit distance from do to low is 2. It's the same as from D to L. That's what it says. And O here, what is it here? Oh, also 2. That's correct. What is it here? 3. Yes. Okay, let's continue. E, we don't have an E here, but so we can always just take the minimum. And you please check whether it's correct. 3, 3, 3. And now here D, okay, the D is the same, so we take 4. And now there's no more D in the rest, so it's always just the minimum of these 3 plus 1, so it's 4, 4, 4. And of course, all we wanted is this thing on the bottom right. This is now the edit distance of the full words from. And actually I did it in the other direction now, which was not intentional, but doesn't matter. This is now the edit distance of blöd and doof. And by the correctness of this scheme, which we didn't prove, we prove it in the algorithms and data structure lecture, this now we know that it's actually 4. You can't do it in less. And how much time did this take? Well, I have a string length here and here, and I made a quadratic scheme and filled out all the numbers. What I did was constant time for each entry. I just had to look at 3 other entries and then compute the minimum. So it's like, yeah, constant time for each entry, and I have length of x times length of y, many entries, plus 1, but this doesn't change it asymptotically. Any questions about this? Let me just check where we... Okay. So, 2 more things before the break. Now, prefix edit distance. What we actually want to do is we want to type only something, and we want matches which are longer. The prefix edit distance is defined as follows. So I have something, the x here is now something shorter. And think, let's maybe do it's maybe this here, right? I have something now, and I'm making a mistake. So this is now my x, and I want to see, does it match Queen Elizabeth II with some, and how many? So I want, maybe this is too small, right? Yeah, this is a lot of mistakes now. Maybe I just make one mistake. Yeah. So here I just forgot the E, and I want now the difference between Quen Eli, where I just forgot the E, to Queen Elizabeth. And of course, Queen Elizabeth II, it's much longer, but I just want to know how good of a prefix match is it. So what do I do? To compare it to, if I want to know the prefix edit distance of this to Queen Elizabeth, I just compare this to all the prefixes of Queen Elizabeth II, and I take the edit distance where it's the smallest. So I take all the prefixes of the second one here, and look at the edit distance and take the smallest value. And let's just do that for an example here. So let's first, 2 examples actually. First, what's the edit distance between uni and university? Just the edit distance, like we had it before, between these 2 words. I see nothing in the chat. 7, I agree. Why is it 7?
Because you basically only have to add diversity
Yeah, you have to add versity. That's right. It's a perfect prefix, so you just leave these three letters, and then there's nothing better than adding versity. What's the prefix edit distance? So for the prefix edit distance, now just look at all prefixes of university and take the one where the edit distance is the lowest. What do you think is the prefix edit distance? Yeah? 0, yeah, that's correct. Which prefix? Uni, yeah. Here you have a prefix which is perfect. So, yeah. So this is so this is now, it's the edit distance of uni to uni. To this prefix, which is 0. Here's another example. Univer, so maybe that's what I typed to university. First, what's the edit distance? Like how we did it so far. What's the edit distance now? 5, I agree. It's 5, right? I mean, it's not, the proof wouldn't be super trivial, but it looks like it should be 5. You want to replace the W by the V. This looks like optimal, and then you add city, S-I-T-Y. What's the prefix edit distance? 1. I agree. It's 1. You look at all the prefixes and take the best one, the one where the edit distance is. Yeah, so it's like the edit distance between, yes, and so this is the edit distance between univer and univer. Okay, that's a W and that's a V. Okay, so, and that's what we want. We want, so when we type something like this here, now we want to get in our list, and we don't get it here in Wikidata, the things which have a small edit distance. Maybe we say up to one mistake is okay, and then we would expect Queen Elizabeth here. And this is what you will do for the exercise sheet. So, all the large web search engines, I mean, not Wikidata or Wikipedia, I think also doesn't have it. It's a pity, but of course in Google you can make mistakes and you will still find the correct answer. So how do we compute the PED? Here we saw how we computed the edit distance. Now the prefix edit distance is defined in terms of the edit distance. So let me just start by doing it and then explain to you what is written here. And let's maybe take the following example. Let's take, let me take Freiburg here. So that's now my Y. And let's take FIBU here. And what do you think, what's the prefix edit distance of, let's say I type FIBU, and what's the prefix edit distance? FIBU, 2. Yeah, it's actually 2, right? It's pretty small. Doesn't look like FIBU is. And why? Because, so the best prefix can actually be pretty long, right? It's this one. It's Freiburg. Freiburg, from FIBU to Freiburg, it's just 2 operations, right? You just add the R and the E, and then you are there. So it's actually 2. So the question is, how do you, well, what you could do is you compute the whole schema, and let's just 0, 1, 2, 3, 4, 5, 6, 7, 8, but we don't do that here. 1, 2, 3, 4. Let's just do the last row And let's do, so I'm not filling this out now, it would take too long. But let's just, the last values are just the added distance from the whole thing, Fibu, to the prefixes. Let's just write the right numbers here without doing the scheme. What's the added distance from Fibu to F? What's the right number here? 3, I agree. What's from Fibu to Fr? I agree. From Fibu to Fre? Also 3, right? From Fibu to Frei? Also 3, I think. It's boring. From Fibu... Because you can replace. Yeah, it's a good question. It's tricky. You have to pay attention. Von Fibu to Freib. What is it from Fibu to Freib? It's also 3, right? Yeah, because the I is now. But this is, and now from Fibu to Freibu, it's 2, right? And now it gets larger again, I think, 3, 4, and so on. So it's interesting, right? This small little problem has interesting properties. So here it even goes down. So you can add a word and then it becomes easier. I think that's correct. Please tell me if we made a mistake here. So now, by the definition, these are just all, if we just look at the last row here, it's just all the prefixes of y, and that's how the prefix added distance is defined, right? It's just the minimum of all the entries in the last row. So this here is the definition of the, yeah? So this is, this is the PED of x, comma, y. And here's one important thing, and then we can almost go into the break. So I can just fill out the scheme as before. It has the same complexity as before. And then I just look at the last row and I take the minimum and I get the prefix added distance. So I don't need a new algorithm. I just do the same scheme, but except for taking the value at the bottom right, I take the smallest one in the value in here. Now I'm saying, let's just take what's written here. Here it says, we only want to know, and this is how it will be for the exercise sheet. We only want to know, let me take a different color here, maybe green. We want to know, is this a match up to 2 mistakes? Is the prefix added distance less or equal delta? And let's take delta or 2. If it's more, I don't want to know how exactly. I just want to know, is it less or equal to 2? And if yes, how much? Then I claim it's enough to look at the first x plus delta plus 1 columns. And what would that be here? That would be x, the length of x is 4, plus delta is 2, plus 7. 1, 2, 3, 4, 5, 6, 7. So I'm claiming I don't have to look. Yeah? No needs. And you tell me why. No need to think about it. No need to look beyond here if I'm to look to the right of this. Now I'm wondering, why is it delta plus 1? So why don't I have to look to the right of this? and by I know I had +1 including 1, 2, 3, 4, 5, 6, 7. Okay, now I know why I had this 1, 2, 3, 4, 5, 6. So if I'm computing the scheme, I can actually save some time. This is actually important when my prefix is small. So this is here the 6th letter of Freiburg. So what I'm claiming here, if I just want to know if the prefix added distance of this to this whole thing is less or equal to 2, I don't have to look beyond this green line. Why is that? Yeah?
If we go right of that, we have more letters to add than we have in the Greek letter.
Yeah, that's exactly right. So starting from R, it's 3 longer than Fibu, right? So whatever I do, I have to add But it's now I'm confused myself because I can take, if I can take prefixes here, it will be among these here, right? Yeah. Yeah, exactly. So I'm already checking all these shorter prefixes here. If this prefix here would be optimal, R or G, it can't be. It can't be one of the candidates because to get from Fibu to Freiburg, I would need 3 added distance operations. To get Freiburg, I will need 4, just because it's 4 longer. And indeed, it's 3 and 4 here. Could be even larger. So if I just want to know, is it less or equal to 2? No point in looking further than this. So no point in looking beyond length of this string plus delta. And the +1 is here because the first column is the empty word column. Okay. So, yes, please?
If we shorten the table like this, will the minimum then always be in the rightest box in the bottom?
No. That's a good question. It's actually, I actually chose this example. Usually it's not like this. This is a bit unusual that it goes down here, which is because of the special structure here. No, it can be further to the left, can be anything. Yeah. I don't know if right now, could it be like all places? That's also, yeah?
If X would be frei, then it would be 0 at the
Yeah, if it would be frei, it would be 0 here. That's true, yeah. I just wonder whether it could be, it can be the smallest anywhere. Yeah, it probably can be. But yeah, it doesn't have to be at the rightmost position. Okay, and now, unfortunately, it's not part of the sheet to implement this, although it would be a lot of fun, but the sheet is already a bit of work apart from that. So we provide the implementation for you. Of course, you can implement it yourself if you want. It's not that hard. You can imagine it. How do you implement this? Yeah, it's just a nested loop where you just implement the recursion, right? And you just look at. So you could just implement it that way, but you don't have to. So we implemented it for you. And actually, Sebastian provided an implementation in Rust because the data set is not so small and Python is really slow with these things. So doing 100,000 PED computations in Python, you feel it. So they're just, and the way it's done, the template which we provide will automatically look if this package here, which you can just install via pip install AD Freiburg QGram utils. If you did that, if the package is there, the code template will use it. You can just look at it in the code And if it's not there, it will use the Python fallback. If for some reason this doesn't work for you, it should be as simple as that. You just install it, then you can use it. Then you will get fast prefix edit distance computation. And also, you will see this in a second, you will need a routine to merge lists, and we also implement that for you. And it's also implemented in Rust if you use that package. Okay, it's time to make a break, but before, is there any question about edit distance before we continue? Okay, no questions, so 5-minute break and then we resume. Okay, we are back online. On to the second part, which is, so how do we now turn this into an algorithm for fuzzy search? And we will talk about qgrams. So here's the intuitive ideas. When two strings have a small edit distance, they will have parts in common, right? So we have already seen that they somehow have parts in common, and we have to formalize that. So for example, Freiburg, Stuttgart, we're not talking about semantic similarity, but of the strings, Freiburg, Stuttgart. Is the edit distance small? What do you think? Just from your intuition, do they have a small edit distance? No, because they're like totally different strings, right? Freiburg, Breifurg, yeah, looks similar, right? Freiburg, Breifurg looks similar. They are similar at many, like there's there's Urk, there are differences, there are similarities, right? So that's what we want to formalize now. Here's a qgram. A qgram is just all the substrings of a certain length. So the q just stands for a length, so these are 3 grams. Does it say here that these are the set of 3 grams? 3 grams. So the q is just an integer, so it's just all substrings, and it's not any 3 letters in any order, it's letters, consecutive substrings of a certain length. Fre, Rei, Eib, Ibu, and so on. Here they are. We define it as a multiset because you could have in a word, and that's something to think about it later, you could have the same 3 gram twice. If it just occurs again later, and then we also want to have it twice in the set. And actually here's an example. Yeah, here we have aber twice. Aber here and aber here. It's just 2 different substrings which happen to be the same. The number of qgrams of a string x is up to you. So obviously it has something to do with the length of the string, but it's not the length of the string, right? Aber is... So what is it? How many qgrams does a string of length x have? People in the chat, you can also... -2 for 3 grams. That's true. Yes, exactly, for q, minus q. So for 3 grams it's -2. So it's not quite correct yet. Minus q plus 1. Yeah. Yeah, so that was proof by incomplete induction. You do it for one example, you assume everything is linear, and that usually works. Sometimes it doesn't, but yeah, you do it for 3, and there it's apparently just... And it's clear, right, because it's not the whole length of the word, because you need 3 letters, so you can't go until the very end. You start in the beginning, and then you have to stop short of the end, because you still need 3 letters. And yeah, and if you just try it out, it's x minus q plus 1. And that's where I should have written this. Okay, let me write it there. It should have been written here. It's x minus q plus 1. Okay, next slide. Similar words have, we said, to have a small edit distance, you have to have stuff in common, and now we can make it more precise. You need to have q-grams in common. And here's the lemma, which we are going to prove. And let's first understand this notation. So let's first understand what's A without B. Let's draw some Venn diagrams. Yeah, let me maybe, where do I draw it? If I have a set A here, and a set B here, then this is the intersection of A and B, and this here is this part here, that's A without B. So you just take the intersection away, right? I think that's simple enough. Yeah, and if the two are very similar, then A without B will be small, because you will be taking most of it away, right? If they overlap a lot, these two sets, and you take B away, then you won't have much left. So what this is saying is, this is not symmetric here, so I'm taking one away from the other. It will be important in a second. So if they are very similar, then this should be a small set, right? Because I'm taking most of, if these are two sets, if they're very similar, then this will be a small set, and this will be a small number, and here it says how small it is, somehow bounded by the edit distance. And let's first do an example and then prove it, but let's first do an example. What's the edit distance? And now we're talking edit distance again. We'll come back to prefix edit distance in a second. So here we have Freiburger and Breurger. Breurger, what's the edit distance? 2. Yeah, I think so too, right? If you have a lot in common, it's actually easy. So F by B and then delete the B. You can't really make use of, I think it's 2, yeah. Okay, let's look at the 2 grams. Let's take 2 grams. I mean, this works with any Q. Let's check if this is correct. Maybe I made a mistake. Looks correct, right? So how many of them do I have? How many are these? I need a number, an integer, preferably a correct one. 9? Yeah, I agree. 9, and let's look at the ones for, how many are these? I mean, I deleted one letter. So I think it's 8, right? It's 1 less. Okay, and now I want to have those from X without those from. So let's see, which ones do I have here? Fr, yeah. This I don't have in, so this remains there, right? So I'm taking away everything from this one which occurs in that one. So let's just do that. So that's fr. And let's see. So re, I also have in re, I also have here. EE, I have here. Ep, I don't have it, so that should be there. Ep. EB. And then bu, I also don't have it, right? And try to understand what's happening here. Bu. And then the others, I think yeah, so ur is there, rk is there, gi is there, er is there. If I have long substrings in common, I will have all the 2 grams in common, right? So, which means the size of this set is 3. And the lemma says, lemma should be capitalized. The lemma here says that Q2 of x without Q2 of y is less or equal, Q is 2 here, I'm looking at Q grams, 2 times 2 equal 4. So the lemma says it's at most 4, it's 3, so it's correct for this example. Do you have any idea? That's a hard question, but maybe you have an idea. Oh, you have the idea before I ask the question? Why it's not, why is it smaller? Why does the lemma only say 4? Yes?
Like we have one letter that is changed, and that can be at most in the number of Q. It is a maximum Q of those.
Yeah. We have one letter that changed. We have two things that changed, right?
Yeah, but for each letter,
Yeah.
each letter can be maximum in Q number of.
Yeah, this is exactly right. So for example, here we deleted the B, and this B affected some of the 2 grams, right? Here we have 2 grams. So the B was deleted, and that's why the EB and the BU have gone away in the other word here, because I deleted the B. And if you think about it, and if you have Q grams, that's exactly what you said. You delete one, or you change one, and it can affect exactly Q grams. It's like you shift a window over there, and for Q points in time, it will be in there. But here it's just one affected by changing the F because it's at the very beginning. That's why we have one less than could be possibly affected. And we'll come back to that in a second. So that's the idea. And now let's, that's what's written here actually. So if the added distance is 1, which means to get from one word to the other, it's one operation. It's either an insert, a replace, or a delete. Then now just think about it. You have your set of Q grams, and now I change one letter. Then this can affect, we just said it, at most Q grams. Which means if you take away all, it's at most Q. The set difference is at most Q. All the others will be the same. So this is basically what we have just argued. Now it seems obvious the rest. Okay, if I have one operation, but there's still something to prove here. Now pay attention. So for the general case, so we have the added distance is k, which means there's a sequence of k operations to get from x to y. That is, if we just take these intermediate things, think of the blöd, doof example in the beginning. Doof, blöd, I think it was doof, boof, bloof, bloef, blöd. So these are my intermediate strings here now. And now I know from each to the next, there's only a difference of the size of Q in the number of Q grams. How do I get to this number? There's something to prove here. And this is what we have to prove. If I have a sequence of sets and I know the difference of one set to the next is at most Q, then the difference from the first to the last is at most the sum of these. So that's what it says here. Maybe I should, so that's even a bit more general here. Let me just write that down. I mean, this here implies, I will now prove this, but let's just verify that this implies if this thing is a subset of this thing, then A0 without AK is less or equal than the sum of AI minus 1 to AI, right? This is just, let's first understand this and then relate it to what I've shown here and then prove it. So this is just saying if this left-hand side is a subset of this, then of course this can't be, the size is less or equal than the size of this. So this is the size of this set difference. And what's the size of a union? The size of a union is at most the sum of the sizes of the things here, so it would be that. And this is what I need, because why do I need this here? This is what I need to show. We have already seen if I have this sequence of string transformations, then from one to the next, it's always just one edit distance, it's one operation, which means the number of q-grams can change by at most q. And now I have to show that from beginning to end it can show by at most q. And so if I show this, then I've shown the lemma. And this here, I mean, let me just, I think you have to convince yourself this is not obvious. It's something we have to prove. You have a sequence of sets. Maybe before I prove it, let me draw it. I mean, what I have now is, let me try to draw it maybe. So I have a sequence. I have a set. This is the set of q-grams of my original string. Yeah, maybe let me call it, so that's my A0, which is my q of the x I'm starting with, the x0. Now I do one operation, now I get a different set of q-grams. So that's now my A1, which is my q of x1. So that's the word I get after one. And now I get the next one. That's my set A2. So I've changed one more thing. I get a different set of 3 grams or q-grams and so on. And now I'm continuing this here. And they are kind of all similar. And this is now my AK here, which is the set of q-grams, q of the y, of the last thing in the sequence. And now I have to prove if the difference of each of these sets is small, then somehow the difference from the first to the last is also somehow bounded by the sum of these intermediate differences. And it's, you could say, yeah, it's intuitive, but I have to prove it. And this is making it exact here. So it's like the step from one to the last is the sum of these. And how do we prove this? Let me just prove it for you. Maybe you have an alternative proof. How do you prove that something is a subset of something else? Well, you take an element from the set of the left and you have to say then it's also in the set on the right. So let's start with an element here. So now we have an element that is in the, let me change that is in the first set but not in the last set. So it's in A0 but not in AK. Let me write my sets like this. A1, A0, A2. Let me just write let me just write it for a fixed k equals 5. So I know that it's in here, but it's not in here. Now that's a typical trick in math. When I know it's in here and not in here, then there will be some point in between where this switches for the first time, where it's because I want to know, I want to say something about two neighboring things. So there will be a point where just in the set before it was still included, in the set afterward it wasn't included. It just has to be like this. Let me just write this up mathematically. So there will be an I such that x is contained in AI minus 1, but x is not contained in the next AI, right? It has to be like this, right? There's just no way. I mean, that's just a fact. Is it contained in this set or not? I know it's contained here. I know it's not contained here. So somewhere along this sequence, I will have a situation. It's contained here. It's not contained in the next one. And so, I mean, it's actually a very elegant proof. I mean, this means nothing else than it's in AI minus 1 without AI, and this means, and that's one of the sets here in the union, right? And that means it's in this union, A1 to the K, because the union is just the union of all these individual differences from one to the next, and that's the proof. Now that's the kind of proof, I can't emphasize it enough, you have to do it for yourself to appreciate it. And maybe what's even better is, first forget everything about what I've just shown to you, try to prove it yourself. Try to prove this lemma for yourself, that's I think the best way to learn. Okay, there's a relation between similarity in sets of q-grams and the added distance. How would I go about proving this? Maybe you'll find a better proof, then tell us. Maybe this is I think an elegant proof, but maybe there's an even better way. Okay, and now let's turn this into an algorithm. So what we have shown here, if the added distance is small, then the set of q-grams is similar. That you should have understood on the high level, and I think it's easy enough to understand this high level. One question regarding slide 19. Why is it stated for not multi-sets? Oh yeah, it's multi-sets. Yes. You are absolutely right, this should be multi-sets. It's no different. It's multi. Absolutely, we need it for multi-sets, but there's no difference. But one has to pay attention to the details. Thank you for asking this. So, that's what we know now. Similar words have many q-grams in common, and we have proven a lemma about it. And here's a corollary now. Okay, how is this... And let's first just see whether it works, and then see how it follows from the lemma on the previous slide. It's actually a simple corollary, it's just a small step from the lemma on the previous slide. And let's just check it first. So what's... how many q-grams did they have in common? Let's just go back one... where did we have these... How many q-grams? What's the exact number of, let's just write this here, maybe in another color. Or let's just do the whole set. Okay, let's... That's now the intersection, q2 of y. How many q-grams do they have in common, these two sets? So what's the size of the intersection? I want to write a number here. Yeah? 6. Yeah, it's the 6 equal signs here. Yeah, it's 6. It's correct. So they have 6. Yeah, they are similar. They have 6 in common. So let's go back to the slide where we have the... So we know that this is 6. And according to the lemma, to the corollary, this now says this is it's the max of, how long is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have already seen that. The other is one shorter. Minus Q is here, we are talking about 2 grams times, and the added distance was 2, which is the maximum 10 minus 4 is 6. And that's correct. So yeah. So this lemma seems to be correct. It says the similarity of these two is greater or equal to that. And now let's prove it. And let's first understand this. I mean, that's also easy, but let me just, if I have 2 sets A and B, what's the time saying? This is the intersection here. A no, not the size of the intersection, but just the intersection. Then the size, I mean, yeah, I don't have to write anything more, I think. If I want the size of A without B, yeah, that I should maybe add again. It's the same picture that I already had. So this here is A without B. How do I get the size of A without B? Well, I just take the size of A, all the elements of A, and I subtract the element in the intersection. I think that should be clear enough. That's just how the difference between 2 sets, so I take away all elements from B and the intersection are related. And that's also where this comes from. Yes, please?
I think there is a mistake in the maximum 10 and 9. I think it should be maximum 9 and 8. Because Q2 of
Oh, yeah.
is not 10 and 9.
Yeah, I was already surprised why there is no discrepancy in where the +1 vanished. Thank you. It's 9 and 8, right?
Yeah.
Yes. But it's still correct, of course. So it's 1. So the actual number is larger, and this is just saying it's at least that large. Five. So this is what the that's just by what we have just shown. So this here minus the intersection, that's just the same as this one, qx without qy. So this here is just this simple set inequality. If I take away from the q grams of x the intersection with the q grams of y, I get the q grams of x without the q grams of y, and this here is just the lemma. It's just the lemma that we have shown, and maybe I write it here. This is the lemma. And now the thing is, we can do the exact same thing in the other direction, because the edit distance is symmetric. We can also just say, okay, if we take from y away the q grams of x and y, then we get all the q grams of y without the q grams of x, and this is also q times. And I think it would be clearer here if I write it like this. Which is then So this also follows from the lemma. I'm just applying the lemma in the other direction. And this here is ED of x, comma, y. And now if you just put these two together, I mean then you just bring this to the other side, this intersection here, then you get this intersection is greater or equal to QQX minus this here. So I just get this once with QQX and once with QQY, number of Q grams here, and both inequalities hold, so the intersection, just notice, right, if I bring this to the other side, I get this here is greater or equal to something. And greater equal to this and greater equal to this, minus Q times this, so it's greater equal to the maximum. Okay. So if I put them together, I get this corollary. Even if you didn't understand the math, and you absolutely have to do the math yourself at home, what does this say? It says, if two words, it just says how many things how many Q grams do two words have in common. And here it says, and if the added distance is small, so if they are similar, then this will be a small term that's subtracted here, and this will be a fairly large number. It's the size of the longer string, right? So just says they will have many Q grams in common. So let's look at the special case. They have the same length, let's say 10, and the added distance is 1. Then this will say they have 10 minus, let's say we're having 3 grams, then they have 3 grams in common. And we have a slide about that. So that's what it says qualitatively. And here's another one. That was for added distance, that's for prefix added distance. That's now, it's, there's a Q missing here. And I have to add it, keep. It's basically the same, except that we don't have the max here. And let's just, Okay, let's see if you can do this by heart. What's the size of this intersection without going to the previous slide? How many 2 grams do these two have in common? Yeah? 2. Which are they? RE and EE. Yeah, let's maybe write them exactly. So it's so this is, yeah, so I mean, you just have to look at these here, the smaller ones, because the, and it should be burger, right? I think I didn't want to, that was not on purpose that I omitted, but it's still correct. Yeah. So BR is not in there, RE is in there, RE and EE. EE. So it's 2. And what does the lemma, what does the corollary say? It says the length of the first one now, Brie, which is 4, minus, oh, and by the way, what's the prefix added distance between the two? What's the prefix added distance? 1, that's correct. Minus 2 times 1, that's the prefix added distance here. And it's 2. So the corollary says these two, because the prefix added distance is 2, do at least have 2 in common, and they actually have exactly 2 in common. There's a space too. And I'm not sure whether I will go through the details of, it's basically the same proof as before. Now you just have to make use of the fact that we have the prefix added distance here. I think you have to do it yourself too. It will not help, I think, if I now explain this in words, what's written here. just to continue and to be able to understand the last part, it's again saying something about, I want to know how many q-grams if the prefix edit distance is small, then I will have many q-grams in common with the word. And it makes sense, right? If I'm a perfect prefix of this one, then all my q-grams here will also appear here. And if there are some small differences, then it will be a little bit less. That's what this says here. So intuitively, I think that's easy to understand. Just the math. Yes? Yes?
The q-gram of x, should this be the q-gram of
Here?
or why is it 4? Yes. Is it like 3?
So what's the question? Oh, you are right. It shouldn't be. Yeah, you are completely right. This shouldn't be 4, it should be the number of 2 grams, should be 3, right? And yeah, you're completely right. But now I can't, because now I have to draw it. What? Wait, now I get my shape. Shape outline. No outline. Some PowerPoint magic. Oh my. You are completely right, thank you. Q2 of x. And x is Brie. Okay, now we, okay. And now, yes?
Now the result of this,
Oh yeah, I need another box. You're completely right. 3 minus it's 1. Yes. But now we know how to do this. Go here. Probably there's also, I think I can fill. Again, outline. No. Yeah, I'm sorry. And now it's 1. Maybe it would have been quicker to delete everything. Okay. Now, maybe you didn't understand all the math, but now the algorithm is simple enough to understand. Now, what we want, let's go back to the high level, to our problem. We have, that's what we wanted, right? We have a big list of words, that's called D, it's our dictionary, and we are given something an X, and we want to find all the words in our dictionary which are similar, which means the edit distance. I will have the same section for prefix edit distance, and the second is below a threshold. So now what I can do, the simple algorithm was to just compute it for every Y, and now I can do the following. I can just look at how many q-grams do they have in common. Is the number, do they have a sufficient number of q-grams in common? And I'm taking exactly my bound, this from the lemma, right? And if this is so, if this is not so, then I know the edit distance can't be less or equal to delta. This is just by way of the lemma, right? And I don't think I will go through the details now. Just understand this qualitatively, right? We have shown that if the edit distance is small, then there are many q-grams in common. And we have shown precise bounds. And for the exercise sheet, of course, you have to make it exactly. Now I'm just checking how many q-grams do these things have in common. If they don't have enough q-grams in common, I know there is no way that they can have a small added distance. This, I think, is simple enough to understand. If yes, that's important. If they have very few q-grams in common, then I know no way they can be similar. If they have q-grams in common, I have to compute the exact value. Because all these were just bounds. There's no formula of the kind, the added distance is equal to the difference, somehow the difference in the number of q-grams. We just know if there are too few in common, the added distance can't be small. If there are enough in common, I have to compute the added distance to check if it's really below that bound. So that's the algorithm which you will implement for the sheet, and exactly the same algorithm for the prefix added distance, just with a different bound here. And you have to, for the exercise sheet, you have to make sure you understand this, because of course if you're making a small mistake here, +1, -1, then it doesn't work anymore. You will throw out things which maybe should have been part of the solution. Oh yeah, that was is there any question? That's the algorithm now. I think that's simple enough, but we're not done yet. There's still, so now I have to check, we have to compute the number of q-grams in common, right? Oh, here's one more detail. We will actually pad the strings with dollars on both sides. So for example, for the added distance, if we have 3 grams, we put dollars on both sides. And we put $2, not $3. And why does this work? Well, the added distance between 2 strings with the padding or without the padding is the same, but this gives us more q-grams. And that's actually, this should have come first here. This is the sentence which I wanted. It's an improvement because with the padding, and we will see this in the last part of the talk. Unfortunately, I am going a bit over time. I'm a bit slow today, I'm sorry. But yeah. So for now, just accept the padding. It will be clear enough I will have an example. It's 4 more slides, and there will be an example. And then I will explain it again why you have the padding. So for now, you just add padding, and it's just 1 less than the q. So if you have 3 grams, it's 2 at the beginning, at the end. And for prefix added distance, you only add it at the beginning. And we will see in a second why. So here's the last part of the puzzle, which you need for the exercise sheet. So the algorithm, there was all this math, but the algorithm was actually quite simple. The algorithm was just check for every word how many q-grams do they have in common. How do I compute how many q-grams they have in common? I mean, now of course I could take my input word, break it into q-grams, take every word from the dictionary, break it into q-grams, compute the intersection, but that also looks pretty expensive. We somehow want to speed this up, and that's what the q-gram index is about. And here's what we do. And you will see how this gives us exactly what we need. We will compute an inverted index, so back to lecture 1, but now it's not an inverted index for words, it's an inverted index for q-grams. And it's very easy to understand. So this is, so for example, this is a q-gram with padding, $fr, and since the padding is here on the left, this says nothing else. A word containing this q-gram, it's just a word starting with fr. So here I have an example list: Frankfurt, Freiburg, Freetown, Fresno. Here's another q-gram, Ibu, and yeah, here I just have the list of all the words containing this 3 gram. So that's a 3 gram index. It's just an inverted index, and it's just like the index we have seen in the first lecture. There we had for each word a list of the documents containing that word. Now we have for each possible qgram the list of words containing that qgram. And of course, like in the first lecture, we didn't actually store the documents here, but we had IDs for documents. For a qgram index, you will have the qgram here, and here you will give each word an ID, and then you will just have list of IDs. You don't want a string here or something like this. So that's a qgram index. Okay, and this I still want to do. This will take a few minutes, but I want to do it anyway, just to show you, and it's also a preparation for the exercise sheet. Let me just copy the code from the, I think it's lecture 1. Yeah, let me just call it qgram index.py, and let's edit it together. And now I'm claiming that I can use, with very few changes, I can do the exact same thing. And let's just do that. And maybe I should, okay, and my index now should get a q here, an integer. Yeah, and it already, and this is my self is equal q. Okay, and now build from file. My class is now called, I'm sorry for the overtime, but you had a whole week without me. So qgram index, build from file, self file name, and I think I will leave out the unit test here. Qgram from given file. Before we do this, we should definitely write a function that gives us the, am I right here? Qgrams. That gives us the qgrams of a string x. Compute the set of qgrams of the given string, and let's do a type hint here. It's a string. I think we here we can, so that would be qi is new new. No, we don't have new qgram index. And we have to say which qgram we want. Let's maybe take 2. Frank, we're a little bit late, I'm sorry. So qi dot qgrams of, what do we want? That's now, okay, now we get fr. Do we want, let me take the unpadded ones for this exercise sheet, for this, what I'm doing now. For re I ip poo. I'm a bit slow today. I think it's the weather. I'm very sorry. Okay, let's maybe also do the ones for no, I think it's enough for. So I need a for loop. I in range. How many do I have? It's the length of the string minus. Yeah, we already had that number, right? It should be this. And here I have my qgrams. And now I append, yeah, I just need the respective substring, I think, right? X, and I think it goes from I, starting from 0, yeah, and here it should be probably just I self q. And we will see in a second whether it's, but you tell me if I make a mistake. Is this correct? Looks correct to me. I hope you can still focus for the last minutes. Okay, let's use this up here, build from file. I will not I will remove the unit test here. So now I have record ID. Oh yeah, I have my for line in file. Yeah, I will not take the actual file. I think I have this. I will just take this file here, right? Where I've already extracted this. For the exercise sheet, you have to pass the real file, but here it's quite simple. So I will. So this is just some name here, which is just. It's just a line. And for qgram in qgrams of line dot lower. So I'm going over the qgrams, and I think that should be self qgrams. So I'm just computing. So my maybe I should do it like this. I don't know if the new line will probably be there, yeah. And so I'm lowercasing this. So now I'm just iterate, like I break the documents up into words. Now I just break the word up into qgrams. And now I just if the qgram is not already in the inverted list, then I create the inverted list for that qgram. We did the same thing. And here, and then I append it. Maybe I shouldn't call it record ID here, but word ID. And here so I'm just giving the words as I encounter them ID 1, 2, 3, 4, and so on, like I did for the documents. And I'm starting with 1 here, and then I hope so it's very similar. I'm using the same algorithm. I'm just calling the things slightly different. And now I think does this work? Did you see a mistake? I hope not. So let's see if this works. Qgram. It worked. This can't be. It's impossible. Let me make a mistake here. No, I'm sorry. I didn't make a mistake. I'm slow, but at least it's correct. Now we can do one thing. We can remember in lecture 1, we just outputted all the the sizes of the inverted lists, so the frequencies of the words. We can do the same thing here. It's not called an inverted index here. It's now called a qgram index for. Now I build it from the input file. Build a qgram index. Qgram. And now I just output the inverted list. And you can already think about which qgram will be the most frequent one. And now that I think about it, I think we should add the padding, right? We should somehow. The padding was, we had $, times, we can just write it like this, q minus 1. Let's just add the padding here. Qgrams append x padded is self dot padding plus x and padding in the end. Yeah, and and this is X padded and X padded. And now we need to add a few. We just need to add one, right? It's dollar. This stands for starts with F, and this here is G dollar. Oh, it's still correct. It's amazing. My coding is better than my speaking today. Okay, and now word. This is not. Yeah, I can name the variable however I want, but. And you think, what's the most frequent Q-gram in the collection? What do you think? If it's 3 gram. And here I need to pass a parameter. I want 3 grams. Okay, does this still work? This can't be Python 3 Q-gram index. Okay, it wants a file name. So now it should compute all the Q-grams and then give me the length of the inverted lists. II is not defined. Here it should be QI. Oh my, so much overtime. But you need to stay 5 minutes longer, but then we're done. Okay, these are all the Q-grams and how often they occur, right? So tsbl occurs in 2 words. I'm just showing the length here, but what I can do now is I can sort by frequency. So I take the tabulator as a separator, and then I want, and now let's see. Now I get them sorted by frequency. That's what I just did. Let's see it whether, okay. It's now 3 grams, right? And this is words ending with A. So that's the most frequent. The most frequent ones are ending with this, starting with C. Now we have ion, okay. Makes sense, right? These are frequent 3 grams we have in our words. And if I don't do this now, if I would plot this, you would again see Zipf's law. And now comes the final 2 slides, and I hope you can bear with me for these 2 more slides, but that way it's also on the recording. So this is now, so obviously you want the Q-grams of your input word. You only have to compute this once. Now what you do is, for each of the Q-grams from the input word, you fetch the inverted lists. And then you compute the union of these inverted lists and count how many. I know what I will do. I will just explain it by example. That's, I think, what I should do before everybody runs away. And the previous slide was just the abstract description of this. So let's assume I type brei, and I want to find all words where this is a prefix match with a 2 gram index up to an error of 1. Delta is 1. So the first thing I pad to the left, $brei, and then I get these 2 grams here, $b brei, okay. Now I fetch these inverted lists. So here the inverted list of $b is everything starting with a B, and so on. Brr is everything containing a brr somewhere, so also Gibraltar, and so on. Now I know that if for any word with these are the bounds which we previously computed, if the prefix instance is less or equal to 1, then they must have at least that many Q-grams in common. So now the set of Q-grams here is 1, 2, 3, 4. 4 minus 2 times 1. Right? Should write that on top. This is what the lower bound gives me. 4. My Q is 2, and my delta is 1. So that what my bound gives me. It's easy to understand now. Don't worry. My bound just tells me if anything has a chance of being similar, it must have 2 grams in common. So what I do is I now merge all these lists. So what do I get if I merge all these lists? In this merge list, we give it to you. I get all the words which have at least one Q-gram in common, right? Any of these here, I mean, these are the inverted lists of the Q-grams of my input words. And some words here I will have several times. So when I'm computing the merge here, I will get Bangalore twice, for example. I will get Beijing twice, it's twice here, and I get Freiburg is I think also twice here. Yeah. So these are the only things. All the other ones I only have once, so I don't have to check them because I've established that I need this at least twice. So for these I actually have to check whether the prefix edit distance is 1 or not. And let's do that as a final thing together. So what's the prefix edit distance of Brai and Bangalore? I hope you're still listening to me. What's the prefix edit distance between Brai and Bangalore? It's 3, right? So pretty bad. We wanted 1. It's the last slide, I promise. No match. Why then did it have so many 2 grams in common if the prefix edit distance is so small? I mean, why was it even a candidate? Why couldn't I throw it out before? Can you see it? It's the last question I'm asking today. Why does it have 2 grams in common, even though it's so dissimilar? I mean, it doesn't have. I mean, it starts with a B, that one it has in common, but it also has a RE, right? Here, the RE, but the RE is in the end, in a position which is not relevant for the prefix match. So it was a candidate, but... What about Brai and Beijing? What's the prefix edit distance? 2? 1, I think it's 1. It's a match. Yeah, Brai and Beijing is actually similar than you thought. So that's a match. So here it worked. So Bangalore was interesting, and Brai and Freiburg is also 1, right? That's also a match. And believe it or not, now we are done. Is there anything else? No, it's just the references. So the exercise sheet is to implement this. I'm very sorry for the overtime, but at least it's all on video now. I thank you very much for your attention, and I'll see you again next week.